Morning, welcome to this lecture on Quicksort technique. The Quicksort technique is an in-place sorting algorithm. It is widely used algorithm for sorting given numbers. So we'll discuss algorithm and the time complexity analysis of this method. So this is a fast sorting algorithm, and it uses divide and conquer strategy to divide up the given array into two halves and sort each of the subarray based on the pivot selection strategy, and then gives the sorted array. So it works by selecting a pivot element. There are four ways to select the pivot element. We'll see one by one. So the array given array is partitioned into two subarrays, and the elements in the left subarray will be less than the pivot, and the elements in the right subarray will be greater than the pivot element. So we recursively solve each of the subarray, sorting the elements, and then it returns the result. So the pivot selection strategy follows any of this method. So either we select the first element as the pivot, or the last element of that is the pivot element. And in median of median elements, we select the middle element of the array. And in randomized quicksort, we select any random element as a pivot element. So randomized quicksort is more popular for complex large data set. Most of the practical cases, they apply randomized quicksort technique, which gives better performance. So let's now compare the pivot selection for various methods. And randomized pivot selection, the average time complexity is big of n log n. In the worst case, it gives big of n square time, and in the best average case, so this performs well. It is easy to implement, and slightly uh, there is a overhead on random number generation, because it has to make a lot of comparisons. Partitioning also, it has to do the pivot selection, and so it is having little bit overhead on random number generation. And in median of the three method, the average case time is big O of n log n. In the worst case, it gives big O of n square time. And so this technique, the median of the three, maintains the balance in the data distribution. It reduces bad pivots also. This technique is slightly more requires more overhead than randomized pivot selection. It requires a lot of comparison due to uh, finding the median and dividing the elements. It requires time for swapping and partitioning. So it requires more overhead than randomized pivot sort. And if you select the first element or the last element as a pivot, then the average time complexity will be big of n log n. In the worst case, it is big of n square. So this is the simplest method and fast for small data set. If you have large data set, it is better to prefer the randomized quicksort technique. And this method, the third method, is very inefficient if you have a sorted array or nearly sorted array. The median method takes big of n time for pivot selection and big of n log n overall time complexity. So this is applied for optimal worst case scenario, and more complex, and so it is also slow in practice due to extra computations. Now let us discuss which one is best method. So randomized pivot selection is better for more practical scenarios. It provides excellent average case performance with reduced overhead on making the comparisons and performing partitioning, and it reduces time and uh, work done to sort the elements for large data sets. In the worst case scenario, we apply median of median technique as the most reliable one, but it has additional complexity and overhead. Now let's discuss the working of Quicksort, mainly the parsing technique. So once you selected the pivot, based on any one of the previous method, any one of the pivot selection method that we discussed previously. So you have to now perform partitioning of the array. Uh, we have to rearrange the array so that the elements in the left array is lesser than the pivot and the elements in the right array is greater than the pivot. So we have to generate like that. Then the parsing procedure works like this. Initially, we set two pointers, left pointer and the right pointer. The left pointer uh, is incremented. It starts from the beginning of the array. Let's say start is equal to 0, uh, and we increment the start pointer, that is the left pointer, until we find an element that is greater than or equal to the pivot. And then the right pointer gets decremented from the n minus 1 position, and it gets decremented until an element until you find an element that's less than or equal to the pivot. So in the next step, if left is less than or equal to right, then we swap the elements of the left pointer and the right pointer. So this process should be repeated until the left pointer exceeds the right pointer. Finally, we swap the pivot element with the element at the right pointer or the left pointer based on the pivot selection strategy. So finally, the pivot will be in its correct position in the sorted array. So next we recursively apply this strategy, Quicksort mechanism, in the subarrays. So one subarray which is on the left will be sorted uh, based on the pivot selection strategy. Then the other subarray, right side subarray also will be sorted based on the pivot selection strategy and the parsing technique. So the Quicksort is recursively applied to each of the subarray, and we finally reach to the base case where only one or zero element will be there, which is considered as already sorted. So this is a technique followed in Quicksort. Let's now discuss one example for this. Consider these elements 10, 80, 30, 90, 40, 50 and 70. Let's choose this last element. 70 is the pivot element. First we set the left pointer from the beginning, that is left is equal to 0, and the right pointer from n minus 1 position, that is equal to 6. Now we have to increment the left pointer until we find an element that's greater than 70, because 70 is a pivot element. So if you see at left is equal to 1, we get the element that is greater than 70. Right, then we have to decrement the right pointer until we find an element which is lesser than 70, the pivot element. So if you do this while decrementing the right pointer at right is equal to 5, we have 50 which is lesser than 70, right, which is lesser than the pivot element. So since left is less than or equal to right, we swap the element at area of 1 and area of 5. So 80 and 50 will be swapped. Okay, so we get 10, 50, 30, 90, 40, 80, 70. And we continue this process until the left pointer surpasses the right pointer. So in the next step, the left pointer will move from left is equal to 1 to 2. So it will be pointing to 30, right, which is not greater than 70. So it will move to the next position. Left is equal to 2, left is equal to 3 now. So that is, it is pointing to 90. So 90 is greater than 70. So now the right pointer will be decremented from right is equal to 5 to right is equal to 4. So at right is equal to 4 we have 40. So 40 is lesser than 70. So now we swap these two elements. So 40 will be in place of 90 and 90 will be in place of 40. So after partitioning, we swap the pivot element with the element at array of 4. So these are the results. Uh, this will give this array. And now you can see the pivot element is in its correct position. The elements on the left side of pivot is lesser than the pivot, and on the right side you have elements greater than the pivot. So if you recursively apply this technique on the left subarray and the right subarray, we will get the sorted array, and the pivot is in its correct position. The sorted array will look like this. So this algorithm, so we pass an array and low index, that's the lower index and the higher index of an array. So this algorithm will uh, do the processing until this condition low less than high fails. So when low is less than high, lower index is less than the high index, then we call the partitioning procedure. We pass this array lower index and higher index. We get the pivot index. So the partitioning procedure works like this. First we select the last element as a pivot. So F high is selected as a pivot element, and we set the left pointer to low is equal to 0 and the right pointer to n high is high minus 1. Okay, we initialize left pointer and right pointer. Now we are checking whether the left is less than or equal to right. If it is yes, then we increment the left pointer until we find an element which is greater than pivot. And then we decrement the right pointer until we find an element which is lesser than the pivot. So if left is less than or equal to right, then we swap the element at the left pointer and the right pointer. Then we move the left pointer to the right and the right pointer to the left. This is repeated. And then we swap the pivot with the element at left pointer or the right pointer based on the pivot selection strategy. So it returns the results. So this is algorithm for pseudocode for the Quicksort algorithm. Now we will discuss the time complexity of this algorithm. In the best case, the pivot divides the array into equal subarrays at each step. So the recurrence relation for this is T of n is equal to Tn by 2 plus big of n. So if you solve this by applying the master theorem, we will get the time complexity of big of n log n. In the worst case, it gives big of n squared time. In the worst case, the pivots may be the last element or the smallest element in the array, so it gives unbalanced subarray. So if you have generate the recurrence relation for this, we get T of n is equal to T of n minus 1 plus big of n. So we apply master theorem to solve this equation, we get big of n squared in the worst case. In the average case, it gives big of n log n because we divide the array fairly evenly and it leads to big of n log n. So this works when you select the pivot randomly from any portion of the array. And coming to the space complexity of this algorithm, in this an in-place sorting algorithm does not use extra memory space for sorting. So it considers the recursion space, considering the recursion depth. It takes big of log n time. In the worst case scenario, if you have unbalanced arrays, then the recursion depth is proportional to the size of an array. So it takes big of n space for that. So this is a more efficient algorithm with an average case time of big of n log n. It performs very well for large data set, but in the worst case, it takes big of n square. When the pivot selection strategy is poor, for example, if you are selecting a first element or last element of the pivot in the sorted array or in the nearly sorted array, then it takes a big of n square time. But the randomized quicksort or the meaning of three pivot selection strategy can be used to solve this problem. We can improve the performance of algorithm. So this and place sorting does not require extra space, and it can be used for more practical scenario. Thank you all.